Hi, my name is Dave Marples, and today I'm going to talk about using various techniques on ARM CPUs, specifically Cortex family, for real-time trace for embedded development. So at NUTEX 2019 in Gouda, I reported on using Orbtools, which was a set of tools which sampled single wire output from ARM CPUs, Cortex family CPUs, for analysing the behaviour of running programs. At that time I said that we were looking at the development of a FPGA equivalent capability for using the parallel trace for full execution capture as opposed to sampling of execution. And today I'll report on the current status of that effort, where we are, where we've got to, what works, what doesn't, what needs to be done. This is being done, you'll see this little logo in the bottom corner, the Orbcode. Orbcode is not a formal organisation, it's just a convenient label for holding this work. And the previous presentation is available at the link here. You don't have to take notes. I've put all the presentation links on the last slide, which we will get to eventually. So in terms of the structure of what we're going to talk about today, let's start off with a quick recap of the V1 capabilities to explain to people the context of Orbtools and what it's there for, and then a quick demonstration of V1 using the new debug adapter. Then talk about Orbtrace, which is effectively the hardware for V2, and then a demonstration of some of the capabilities we get with V2, or V2 upcoming if you like, before we do a wrap up at the end, because doing a wrap up at the beginning wouldn't make too much sense. So when we started on this, I had a definition of a rationale, which basically said you can write code that's as good as you like, but you need to verify and validate its operation as well. How many times have you written a piece of code and over time discovered that it's not working in the way that you expected it to? You may be getting the correct results or the expected results, but the way in which it's reaching those results is not the way that you thought it would. Maybe it's just me, but that does happen far too often to be comfortable. We don't know, most of us that work on embedded systems do not know exactly how busy that processor is. Is it running flat out and there's no headroom left, or is it very idle, very relaxed, and actually there's plenty of room for adding more functionality or whatever it happens to be? So visualization and instrumentation, as far as I'm concerned at least, they're at least as important for writing good code, or achieving good product, if you like, as the compiler and the OS on which it runs. Everything I present today is going to be OS neutral, but I'm going to apply it to the NUTEX use case. It doesn't matter if you're running bare metal, if you're running on FreeRTOS, you're running on NUTEX, running on Zephyr. This stuff is interchangeable and can be used in all of those environments. So we'll start off with a quick recap what Orbtools version 1 can do, and this is using the SWO output. So what is SWO? SWO is single wire output, and it's available on Cortex-M3 and above CPUs, and it's basically this pin here, the trace SWO pin. On an STM32 that would appear on port B3, and the data that comes out of here can be formatted in two ways, in a Manchester encoded stream, or rather more conveniently as UART encoded frames. What this means is that you can just plug a TTL UART onto port B3 and you get trace SWO out at some bit rate or other, which is reasonably programmable. Unfortunately, that stuff is encoded, and so the job of Orbtools is to decode all of that information and turn it into all that data and turn it into useful information for presentation to the programmer. Where does that information come from? Well, three places, or a couple of places mostly for the purposes of our discussions. The ETM, the embedded trace macro cell, which is an exhaustive trace of all the steps your program goes through, and the ITM, the instrumentation macro cell, which is much more focused on debug strings, sampling the program counter and things like this. as you can imagine, the amount of data which is generated by the ETM is orders of magnitude more than that which is generated by the ITM, and indeed for Orbculum version 1 and in general for any probe that's using SWO, they only focus on the ITM flows. Orbculum version 1 only focused on the ITM flows through the system. It did not consider the ETM flows. The ETM flows generally have to use this alternative presentation, which is a parallel presentation with much higher bandwidth. In fact, it's parallel and DDR. We'll come on to talk about that later. But for version 1, we did not use the parallel capability. We plugged a UART or some equivalent device onto TraceWO and use the capabilities there. In terms of what the architecture looked like for version 1, then you had your target, which was generating an SWO feed. These are the UART frames coming out of there, and those plugged into the Orbculum software itself. Orbculum exports a TCP/IP actually port socket to which the various clients can connect for doing different things. OrbCat and OrbFIFO for simple multi-text channel variable output, things of that nature. Orbtop for processing the program counter sampling information, and Orbstat for doing various statistics analyses and things like that. It's worth noting that the control and debug capabilities of the processor, which are generally exercised via GDB or something similar, are independent of the SWO path. So you've got your control path, which is bidirectional here, JTAG or SWD for connection to the target, and the SWO is independent of that and completely separate. And there is a little bit of tension in the distinction between these two things, because sometimes it will be quite useful for the SWO to inform the GDB for various purposes. So let's go on and talk very briefly about what can be done with these kinds of tools. I'm not going to go into this in a lot of detail because the presentation will become over long, and you can go back to the previous presentation for a demonstration of using these tools, or indeed you can go to the Orbculum codebase where you will find documentation on how to use these tools and what you can do with them. So OrbCat and OrbFIFO split out the 32, there can actually be more than 32, but for our purposes 32 debug channels which are independently set over the sent over the ITM link. So you can send strings, you can send ints, you can send characters, whatever it happens to be, with simple primitives which go over the port and are multiplexed onto that single serial flow that comes out of the SWO pin. And one of the things that Orbculum does using OrbCat and OrbFIFO is to allow you to process these, for example, using printf style structures. You can process these things and turn them into rather more sensible strings which make sense to human beings. You can separate things out, so you can have certain information sent to certain debug logs and not to others, and so on and so forth. And then OrbFIFO excuse me, basically gives you an exhaustive catalogue via FIFO of the events that are generated by the CPU. So going into an interrupt, coming back out of an interrupt, going back into a thread, and so on. These are not operating system primitives. This is what the processor is doing, going from exception mode, interrupts called exceptions in ARM, into runtime into run mode, and so on, backwards and forwards between the two. Those are the kinds of capabilities you get. It's equivalent, pretty much everybody puts a UART onto their embedded design so they can see what the device is doing when it's executing the program. It's the equivalent of a UART, but it's an output only device and much higher bandwidth, or a potential to be much higher bandwidth depending on what hardware you're terminating the flow with. Moving on a little, we have Orbtop, and this is the one that generally gets the airtime inside of Orbculum version 1. And what this allows us to do is to generate a top like trace of where the processor is spending its time. And this is done by sampling the program counter and outputting the program counter on a regular basis, or if the processor is sleeping, a special code to say, hey, we're asleep, we're not doing anything. By reconstructing those program counter samples and referencing them against the ELF that makes up the executable, you can turn that back into individual line numbers or files or functions to be able to see what the CPU is doing. And then there's some nice eye candy to be able to plot out to graphs and so on and so forth, lots of bits and pieces that you can do of that nature. We've also got orbstat, which can do the processing of these raw flows into higher level constructs. So if you instrument the routines for entry and exit to a function and log the fact that you've done entry and exit to a function to the ITM, then you can use that to reconstruct the calling flow of your program. So this is an example of a very simple, this is actually a FreeRTOS thing, as far as I can see from the structure of the primitives. You can actually use this to reconstruct the structure of a program flow, how many times the task switch context called into task out, for example, how many times we responded to an interrupt for either the USB or for the timer. And you can very, very quickly get an idea of exactly where is my program spending its time. And there are multiple views of this. Other people have made some quite nice post-processing visualizations, so we can see things like hot paths through your code. So you can see where your code is spending all of its time. If you've run out of time, this tells you where you need to focus so that you can dig in more detail and fix things up which need some special attention. These are quite static, they're single graph presentations of what's going off in your code with flow down. If your program becomes moderately complex, that becomes an issue because you end up with a graphic that's way too big and you can't drill down into the particular bits and pieces you want to. This does happen on the PC side as well, and people have built stuff to address this problem, and the most well-known one is kcachegrind. Kcachegrind allows you to fly around, effectively around that graph, this graph that I show you here, by clicking on individual boxes, and from there seeing what the relationship of that box, those boxes are to the other boxes inside of the system, and how this corresponds to source code. So I have here the source code for an individual function. This is the relationships between them, and these are the counters in various ways, shapes and forms for presenting what your program is actually doing. So you can fly around inside of your program and understand where it's spending its time, what instructions it's spending its time on, or what functions, sorry, not what instructions, and then be able to look to see what you need to optimize. Need to emphasize the fact this is not instruction level instrumentation, this is function level instrumentation, and it requires some instrumentation of your code base in terms of the headers and footers of the functions themselves in order to operate. And the information on how you do that is in the Orbtools website. So let's look quite briefly at this thing in operation, and rather than using the UART itself, we're actually going to use the new Orbtrace hardware, which gives us, you remember on the orbtop picture I was showing 4,500 or so samples per second. With the new hardware, which I'm going to talk about after this the demo, we can get much higher flows, and I think in this demonstration you'll see we're doing about 150,000 PC samples per second. So let's do a quick demo of this basic functionality.
So what we have here is a bog standard STM32F427 chip on a small board, which we call the mule board, connected to the Orbtrace device using the extended debug and trace interface. That probe exports a SimSys DAP interface, which we can connect to using anything that will talk to SimSys DAP, such as PyOCD and OpenOCD. We're going to use OpenOCD today. Oops, if I can type. In fact, well, just to show you that PyOCD works as well, that will connect perfectly well. And there we go, it's connected and it's initialized onto the device. But that's not the one I'm interested in using. Let's use OpenOCD for the purposes of this demonstration. Okay, so it's connected, 10 megahertz connection speed, and we've got hold of the standard device with 6 breakpoints, 4 watch points, all looking good. I already compiled a NUTX image, and I'm going to burn that onto the device now using GDP. So there's a setup script already running, so ran, and we will load onto the device itself now. And it takes a few seconds to erase, and then the actual loading process and burning onto the chip. It's done. Now what I'm going to do, because this thing is going to connect under does a connection under reset, I'm going to cheat slightly and restart OpenOCD, and then restart GDB as well, and then continue. So now, if we look at where we are, we're in STM idle. If I go into mix mode, you can see that most of the time I'm spending in WFI mode. So this is all working perfectly well as we would expect it to. What I should be able to do is connect to the USB port. So let's bring another session in here and do a cu-s/dev tty ACM. Don't know which port it's connected to. Let's assume it's 0. So just a bit of a guess. Oh no, sorry, -L, not -S. Oh, there we go. We were lucky. We got the right one. Okay, so we've got a nutshell up, which is working perfectly well, and we can obviously run OS test and so on. However, what gets more interesting is when we bring Orbmortem into the mix. So let's bring another window in, and in this window we are going to run the Orbmortem server. So that's connected, and it's now issuing 2 network interfaces, which we can use for communication with the to observe what the device is doing. So let's bring one more window in. It's getting a little bit crowded, but we'll cope. And in this window, we will run, if I give it a little bit more room, we will run Orbtop. This is a program some of you have seen previously, and Orbtop tells me that the device at the moment is pretty much asleep all of the time. It's not doing anything very interesting. So now let's run OS test. What I have done, oops, I'm not sure what happened there, but let's carry on. We don't want to stop that. We'll run OS test and just let it run through its application. So there we go, it's on its way, and as you see in here, we're doing it per second at the moment. We still see the majority of the CPU is sleeping, but the program is running, and we see the activity as it's running, as it runs through. So we start to see effectively a top, which is what we're looking for. I will confess that I have slowed the CPU down by a factor of 4. It's only running at 48 megahertz, and the reason for that is, if you see there, we are sleeping for 99% of the time. If I run the CPU at full speed, I actually can't see any of the instructions. There just are too few of them, which gives you some idea of just how busy these devices are capable of being, or how fast they're capable of being. Okay, that's the first step. That shows the use of Orbtrace just as a pretty standard debug interface. If I again come to here and do Control-C, refresh the display, and we can still see we're back in idle mode, and then we can continue. Obviously everything's frozen here. The sampler is still running, but there's nothing to sample anymore, so it's not going to get too far. But when I continue, then everything carries on as it was, and we still have the nutshell running over here, and we still, you can see we're spending a lot of time in memcopy. Well, a lot of time, 0.35% of our time is being spent in memcopy, and magic is happening over here with all the various activities that are going on. So that's just showing you using Orbtrace as a bog standard debug probe like any other debug probe. Oh, alongside, of course, traditional orbculum.
Okay, so where we got to in that previous presentation and the end of this recap part of the discussion is orbculum working perfectly well over the traced SWO output, and the possibilities and the potential of these trace feeds or these data feeds off the CPU having been demonstrated. So what looks very juicy and enticing is this up to 4-bit port available here, the trace data port. And this stuff the data comes out of here at different clock speeds, but DDR up to 4 bits, so effectively 1 8-bit byte per tick of data falling out of that port. And these data come out so quickly that there aren't any conventional interfaces that will pick this stuff up easily, and so we end up having to use an FPGA. And that's really where we got to the last time around. We were saying, okay, this is pretty cool as far as it goes, but if we want access to the speed of data that's going to fall out of the ETM source, then we're going to have to go FPGA. So the future at that point promised full profiling of code runs, because access to the ETM allows us to do that. The ability to record things pre-trigger. So I've crashed. What was I doing before I crashed? Non-intrusive, full-speed code path observation, so we can do things like code coverage to understand if our test plan is doing what we expect it to. And of course we get the other stuff like the full-speed software channel output, the ITM outputs that we were already using, and triggers. So let's go on now and talk about the new stuff, which is Orbtrace, Orbculum, and Orbtrace and Orbculum V2 sort of fit together. So how does this new capability change things? Well, here's Orbtrace as a thing, a big orange block just over here on this side, and we add in the parallel trace capability. Now normally on a Cortex class target, the connector would be a 20-pin 0.05 2-row header, and so on that header alongside the parallel trace would also be the JTAG or SWD, and it would be incredibly inconvenient to only take the trace and not to be dealing with the JTAG and the SWD as well. So we included in Orbtrace this capability and exported a SimSys DAP driving interface to it, so that your debug stub and GDB can plug straight into here. And typically this debug stub would be OpenOCD or PyOCD or Blackmagic Probe or whatever you wanted, or Blackmagic Probe hosted I should say, or whatever you want to use in order to realize that functionality. So we end up with this, Orbtrace becomes a single device. You've no longer got multiple cables dangling off of your target in order to realize this functionality. Orbculum itself plugs into Orbtrace and gives us all of the flows we previously had. So we have the debug channels, the PC channels, we can do the post analysis and so on. But we can do this much faster now because we've got these information flows coming over the 4-bit port rather than over the UART coded port. So we get faster, more data and so on. And as you saw, it was actually 187,000 PC samples per second compared to 4,000, 5,000 PC samples per second when using the UART. But we now have access to the ETM, and the ETM gives us a new flow, which is the full program flow. Now what we've done here is we've implemented a piece of code called Orbmortem, which is for post-mortem analysis of programs after they've died for some reason. And this is new. This we couldn't do any other way. You couldn't even easily do this with, well, you couldn't do it at all with something based around interrupts and processing of interrupts, which you can use for realizing some of this functionality. So Orbmortem is the first thing. That's the, if you like, the flagship product, which is going to show you what Orbculum can do when used with Orbtrace. But it's not the limit. We can use this full program flow for all sorts of other things that we haven't yet implemented. And one of the beauties of doing all of this stuff open source is that other people can pick some of these things up and scratch their own itches and do things that they want to do. So all of this stuff is open source. You can go to the website, download it freely. It's open under very open licenses, so you can exploit this, extend it. And the only thing we would ask is if you benefit from this, that you give stuff back when you're able. So you add in functionality to the device or to the code base and make it available for others to use. So what does the device look like? Well, this is Orbtrace Mini. The implication being that there'll be a maxi or at least a full fat version at some point in the future. We'll worry about that later. But for now, this does everything we want it to be able to do. It has a Lattice ECP5 FPGA, which does the heavy lifting from the 20-pin trace plus debug or 10-pin trace only, debug only port. It does level conversions for talking to targets which are working at different voltages, and we have a number of other pins, various LEDs. We've got 8 megabytes of RAM available, and I think 4 megabytes on the current version of flash for holding the configuration and programs. And this communicates to the outside world over a USB high-speed link. So these the nominal speed of the link is 480 megabits per second. We can get around about 400 megabits per second of real-world data out of that flow. The Orbtrace hardware is a very good example of the benefits of open source, and was designed by Veghard to plug into the Orbculum overall system. And very shortly, these will be available from his web shop. We are trying very, very hard to keep the price down. The equivalent functionality bought commercially for Trace in the open market is around about $1,500 to $2,000. We've been pushing very, very hard to keep the price of this down, and these will be available for 100 euros. Or the equivalent in dollars, $120, and very slightly less in pounds. But the pricing will be in euros. So we will have these available. We've managed to source enough hardware to build 100 units, even in these chip constrained times. And what we've also done, because these things are going to be quite valuable, is we've made a case for them, which is a 3D printed case. Now, the 3D printed sort of implies maybe not the very best quality and so on. That's not the case here, not the case for the case. This is a SLS printed 3D printed case, and it's properly tough. And the intention is that you can throw this thing into your rucksack or your bag, and it will be protected. So all of the pins will be are appropriately recessed, and you can, to be honest, this thing you could probably knock nails in with it. It's nice and solid, very high quality case. If you're going to get this hardware, I'm going to finish with the advert soon, but if you do get this hardware, highly recommend you get the case with it in order to keep it safe and protected, because you won't be able to get hold of spares for quite some period of time until the chip shortage eases a little bit. With the case and the board, and it's a project, not a product, so you'll end up assembling the thing yourself. That will be about 130 euros, because the cases for this quality, the cases are not that cheap to make. Okay, so what can it do? We can power the target, so we can we can set the voltage and measure the current, so we can do that quite quickly, so we can watch what's going off on the target device, what its power consumption looks like. And we have all of the various programming pins for either JTAG or SWD are available on the 10 pin and the 20 pin connector, and also available through individual 0.1 inch headers as well. And you can also use this for programming other devices like FPGAs, and in fact Orbtrace is self-hosting. You can use Orbtrace to program Orbtrace, and this is the preferred way of working nowadays, using Open FPGA loader. You can also monitor the power from or the voltage level from the target itself to see how that's behaving, and there are various diagnostics and monitoring going on. Everything should have a general purpose button, so we've got a general purpose button. The 4-bit parallel trace, which appears on the 20 pin connector, plus debug on the 10 pin. Anyone that knows these connectors in reasonable detail will know that the right hand end of this larger connector is actually a replication of the smaller one. And indeed, with this setup, you can plug your existing favorite debugger into the 10 pin header, and it will pass it through to the 20 pin header, so you can use your existing debugger for debugging and use Orbtrace just for the tracing if you want to do that. But if you do want to use it for debugging, we use SimSysDAP, either for SWD or for JTAG. We also have some general purpose I/O, and these will eventually, they're not implemented or they're not operational right now, but they will be used for serial SPI, triggers, things of that nature. These are bidirectional. You can use them for outputs or for inputs. In terms of the architecture inside of the device itself, this is roughly what it looks like. So we're using MyGen and NMyGen for implementation, also clean Verilog. And we're inside of here within the Litex environment. We have a VEX. Some of these terms will mean nothing to folks. That doesn't matter too much, just so you can understand the overall structure. We have a VEX RISC-V CPU in there, which we're actually not using at the moment. Everything we're doing at the moment, including the SimSysDAP, is done in gateware. It is not done in software. So this thing is pretty much sat idle, but our expectation is that you'll eventually be running Nutex FreeRTOS or something on there for various standalone applications. I have some RAM connected to it, the GPIO. We also have the ability to connect to an LCD, which we're not using right now. In terms of the Verilog side of the fence, we have the trace interface for taking the data from the device and reformatting it and making it available to the PC. We also have the debug interface, which can do SWD or JTAG for debugging. These are the two physical interfaces here. And then over in MyGen, we have the SimSysDAP capability and Luna, which offers the USB connection. And that all plugs into a bog standard LP to communicate at USB HS rates with the PC. So in terms of the first use of this hardware, we're using it for a program or for a part of the Orbculum suite, which we call Orbmortem. Orbmortem is, as its name implies, all about post-mortem analysis of your program when it's died. So when your program has died or stopped running for some reason, either you've held it specifically, or it's hit a breakpoint, or it's hit an exception or something like that, a hard fault handler, for example. And what it will do is maintain a constant ring buffer of the last amount of execution, by default 32K of execution, but it can be any size you want. And then when a hold occurs, it post-processes that buffer to say this is exactly what was happening when the program stopped. So you get a trace, a post-mortem trace of everything that your program was doing up until the point that it died. Not what you thought it was doing or what your program listing said it was doing, but what it actually did, the specific instructions in real time that it executed. Now you can imagine how useful that is. If you've ever been stuck in the hard fault handler and wondered how you got there, if you'd ever had a line of code executing, you didn't know why it was executing, if you'd ever wondered where your CPU is spending all of its time, this is where Orbmortem comes in. So now what I'm going to show you is a quick demonstration of Orbmortem in use, and again as a a live demo if you like.
Okay, this is pretty much where we were at the end of the last episode. We've got orbtop running, showing us what's going on, which is not very much. The CPU is basically idle, and we've got a nutshell running, talking to the device. If I make the device a little busier, just enter a few enters in there, maybe a little busier, then you start to see some activity appearing in the orbtop session. What will be really useful is to be able to see the interrupts or the exceptions, as I want to call them, that are going off on that CPU. And we can do that inside of orbtop with the -E option, and that will tell us, hey, this is what's going on with the exceptions. So we've got exception 15, which is occurring 100 times a second. That's hardly surprising. Exception 15 is the systic, and we expect to get a systic every 10 milliseconds. So this is perfectly reasonable. It makes perfect sense. If I start to give the thing a little bit more work, we've now got USB interrupts and all sorts of other bits and pieces, and we can start to see those other interrupts occurring in the table. So again, more work, and you start to see it appear in the orbtop output. However, it would be really nice to go into more detail than that and see the detail of what was going off with the instructions, and that's where the new tool, Orbmortem, comes in. So, Orbmortem, as it's going to start it up, Orbmortem, as its name implies, does things after the death of your program. So that death may be due to an exception condition, it may be due to you just stopping it using Control-C, maybe due to a breakpoint or whatever. What Orbmortem does continuously in the background is maintain a ring buffer of adjustable size, programmable size, of the most recent instructions that the CPU has been executing. And then when you stop it, it decodes that buffer and tells you what the CPU was doing until the point that it stopped. So initially, let's just put it on hold. Let's hold it there. And you can see those instructions. We can search up through them. Let's look for an exception entry, because that's more interesting. Okay, so this is an exception entry 15, is a systic interrupt. And we can see before we went into the systic, we did all the various things we have to do, prepared to be in idle mode, and eventually we did a WFI, and then we basically just sat waiting for an interrupt, and at some point later an interrupt arrived, which was 15, which is the systic. So this is not showing you what you think your program should do or what's written in your text. This is what your program did. This is every instruction, and you can look at this in mixed mode, where the files and the source lines and the assembly lines are intermixed. You can look at it just in source form. May not syntactically look right. For example, there can be all sorts of strange curly brackets, because this is the analysis of the source code of the individual instructions that ran. You can look at it in object code. You can look at it as individual instructions that ran or did not run. And you can most normally look at it in mixed mode. What gets more interesting is when you want to look around inside the code. So for example, you can put markers on it. So I'll put a marker for 0.2 there, I'll put a marker for 0.1 here. I can move it to the beginning of the buffer and go to 0.1, go to 0.2, change modes. And then we can also do things like, for example, there's an interesting one, there's a watchdog timer. So we'd like to dive into that and say, in the source code, what does that correspond to? Because although that line is executing, I can't see it in the context of the program. So we just hit the right arrow key, and it will take us directly into that piece of code which it pulls from the disk and delivers it to you, so you can see what's going on. So you can dive in and out of code. That's a least critical section there, so we can look at where that was called. We can dive in and out of code as we see fit, as and when we want to. As we debugging, of course, we know perfectly well that it's quite normal. You don't just want to look at your code, you maybe want to make a small change. So if you hold down the shift key and press right arrow, it will start your favorite editor. And in this case, my least unfavorite editor is Emacs, so that's the one that it starts for me. I can go in and make the change and come back out and recompile or whatever. So the idea of Orbmortem is at any point in time, whatever my program is doing, When it stops, it tells me why it stopped and allows me to dive in and analyse that in more detail. So just for an example, just a simple example, somehow GDB's ended up out of step. Let's just stop in clock timer, which is a routine. Well, we can just do Control C. Control C tells me that's just what it happened to be doing at the point where I hit Control C, which was a WFI, which is what you would expect. But now let's put a break on clock timer. Okay, we've got a break in there. Let's unhold it. So it's now waiting because there are no instructions coming in. It doesn't know what to do, so it just sits there waiting for some instructions. And I tell the program to continue. It runs for a very short period of time, and again it hits the break point. And now what I've got is the history of the instructions until that point in time. So my last instruction should be just the beginning of clock timer. That looks promising. Dive into there. There you go. What clock timer does is increment the system timer. So yeah, that makes sense. And that's what these are the instructions for the entry. So this all works perfectly well. Now, of course, you can use this just as easily you can put a breakpoint on the hard fault handler, so you can see exactly how you ended up in the hard fault handler, or how many times have you been coding, landed in a particular location, and thought, I don't know how I got here. I don't know what combination of things happened that allowed me to get to this point. And that's exactly what Orbmortem allows you to do. It's a full instruction by instruction analysis of exactly what your program did do, not what you thought it should have done. And that's why it's useful. Okay, so in summary, Orbtrace allows you the ability to trace individual instructions on anything Cortex-M3 and above. We've concentrated on M3 and above for now. A lot of the things that can be done with ITM, you can do other ways with interrupts and with program code. You can't do things using the ETM in the same way. It's simply not possible. So Orbtrace, as opposed to just straightforward orbtools using the ITM, gives you a novel capability you can't really get any other way. We've demonstrated it for post-mortem analysis, but we can do a lot more. The hardware has a lot more capability on it. We aren't using those GPIOs yet. We aren't using the embedded RAM. We aren't using the RISC-V. And on the other side of the board, the bit I didn't show you, there's a 50-pin expansion connector as well. So there's plenty of headroom and expansion for doing more things that we don't do right now. Code coverage, reverse engineering, hot path detection, snapshotting, all sorts of bits and pieces you can do that we haven't done historically because the tools for doing so have not been accessible at a reasonable price point. And we've made all of this open source, so please do come along and help. And it would be greatly appreciated. Help would be greatly appreciated. So I think with that, thanks for listening. There are all the links to orbtools and Orbtrace. Some people get confused between the two. Orbtrace is the hardware, the device that I showed you, and Orbtools is the software suite which does both the ITM decode, which can use a device like a UART or a Sega J-Link or whatever it happens to be, but it can also plug directly into Orbtrace for the high-speed decode functionality. That hardware will be available. They've just finished manufacture with the EMS and they're being shipped to Norway as we speak. And that hardware will be available in the next couple of weeks. There is a limited amount. We only have 150 pieces. Probably going to be a long time before we get any more. So if you are interested in that, there is a hardware waiting list, which is the Orbtrace issue 1. Please add your name to that list if you are interested. If you're intending using Orbtrace, then you need a single unit, probably with a case. If you're intending developing and wanting to work with the FPGA and so on, then we'd recommend you get a pair so that one can be used to reprogram the FPGA of the other. You can reprogram the FPGA over the USB interface, so that's not a fundamental constraint.
but just so you're aware. I think that's all we can usefully cover right now. So with that, I'll close out, and thanks very much for listening.